Yeah. Uh, Hi team. Very good morning. Like I'm changing the slides. Are you able to see the slides? Please, anybody, please respond.
Yes,
Yes,
sir.
sir.
Okay. Okay. It's good. Now let's go to like nice margin. I mean continuation, guys. Uh, yeah. Team. In previous class, we have discussed about static discipline. Like if there are vendors, being a designer, how can you choose a vendor based on the VOH, VOL, and VIH, VIL values? Hope you know them. Just for better understanding, just for a while, just we are revising the static discipline parameters. They are simply like you can see this figure. This figure itself gives you the clear understanding. If there are two buffers connected in cascade, the left side one is a driver element and the right side one is a driven element. The left side buffer is transmitting the data so that you can get the output voltages. Either it is a VOH or VOL. See, if it is a VOL, that is max output voltage logic 0. It is representing the logic 0, the max voltage. Remember, being a 0, uh, it must not more than this VOL. That is a criteria. Similarly, VOH as that is a minimum value for the logic 1. If it is to be considered as logic 1, that value must be beyond this VOH or is equals to VOH. Similarly, the right hand side buffer, which is a input voltage to that driven element. So as it is receiving the like signal, it could be like considered as input. Similarly, like maximum and minimum. Now, hope you know we have discussed about in between driver and element and driven element. Noise will be added during logic 1 transmission. Negative noise will impact. Similarly, during logic 0, positive noise will impact. According to that, you know the indeterminate region, the prohibited region will reduce. So that here the difference between the VOH and VIH is high noise margin. Difference between VIL and VOL is low noise margin. Hope you know whatever the values of high noise margin, low noise margin, we need to consider the the minimum value of either NMH or NML. So that if you take minimum value, that will be applicable both in noise high margin noise margin high, noise margin low. This fundamental is very important to continue module 2. Actually, this entire concepts comes under module 1 only. But when you go to the module 2, these static discipline, VOH, VIH values will be important. This will be carry forward. Remember, we have a clear roadmap to complete or to make you ready to enter into physical design. Remember, every module is interconnected with another module. Okay, now let's get started. Team, here we want to know about static discipline for buffer. Yeah, we know regarding the buffer, output is same as input. Now, you know, the input voltage less than or equals to VIL. See, what is VIL? The max voltage, which can be considered as logic 0. So any voltage less than or equals to VIL can be considered as logic 0. So to the buffer, if input is logic 0, output must be logic 0 only. Hence, remember, output voltage will be less than or equals to VOL only. Similarly, if at all input voltage is more than like if it is input voltage is more than VIH, then yeah, if the input voltage is more than VIH, then obviously it can be considered as logic 1. For logic 1, the output is also logic 1. To be considered as logic 1, the output voltage must be greater than or equals to VOH. So what I mean is, here input voltage is not in your hand. How much voltage you may get it because of the noise. Sometimes there is a noise voltage of 0.5 volts. Sometimes there is a noise voltage of 0.3 volts. But our criteria is, if at all input voltage is less than or equals to VIL, that is a valid input. For a valid input, there must be a valid output. And that output is less than or equals to VOL only. This is what for buffer. And as per the conditions, you can relate the figure. There the input voltage you can see here. Just a second. Yeah, see here. This is VIL. If the input voltage is less than or equals to VIL, then it is logic 0 only. Then output voltage also must be 0 only, means that is less than or equals to VOL. Similarly, if at all input voltage is more than VIH, then output will be more than VOH only. Here you can see that's what here you cannot like guess or you cannot predict whatever the input voltage which is coming. We need to see whether it is less than or equals to VIL or not. That is greater than or equals to VIH or not. That's it only. Similarly, you can see for the buff like a inverter as well. Just a second. Yeah. Yeah. You can see you can see for the inverter. See, this is the inverter. Just a second. I'll rub this. Yeah. Yeah. Now you see for the inverter. See guys, if it is BTech academics or BE academics, you can call this gate as a NOT gate. But when it comes to the VLSI industry, I suggest you to speak like inverter only, not gate. I told you so many times. Again, I'm telling you, the terminology which we are using is very important, especially in corporates. Now, coming to the point, you see the inverter where input is A, output is not A. That means A bar, A complement. So if input is 0, output must be logic 1. If input is logic 1, output must be logic 0. That means if Vin is less than or equals to VIL, it could be considered as logic 0. Then output must be logic 1. Means if it is logic 1, the minimum value is VOH. Even it could be more than that. Hence, we are giving you the static discipline for inverter simply if at all input is less than or equals to VIL, then Vout must be greater than or equals to VOH. Similarly, if Vin is greater than or equals to VIH, which is represented as logic 1, it can be considered as output logic 0. That means less than or equals to VOL. See, you need to understand, I mean, this diagram. See, this one. See, this figure. If you understand this figure, it's very easy only. Now, let's come to the point. Team, here we want to know about one important concept called signal restoration. Remember, if the design or the elements following the static discipline, even though signals gets distorted because of the noise, nothing will happen. They restored back to their original levels. That is what signal restoration. If someone asks you what is meant by signal restoration, you can tell the definition as it is. Now, let me give the description for that signal restoration. See team, here there are two buffers. one driver element, one driven element, where the driver element output is X, the driven element input is Y, and the driven element output is Z, X, Y, Z. Now let's assume VOH is 4 volts, VIH is 3 volts, VIL 2 volts, and VOL is 1 volt. Of course, let's assume noise margin is plus or minus 1 volt. Means the noise margin, the noise voltage is maximum plus 1 volt or the minimum minus 1 volt. Now let's come to the point. See, there is a graph you can see here where the graph X is VOL value is 1 volt, VOH value is 4 volts. Now here here, huh, here the noise is included. You know, here I'm trying to write there is a noise. Yeah, noise may interrupt the signal, so that let's assume plus 1 volt during logic 0 transmission, because we know during logic 0 transmission positive noise will show the impact, so that this one becomes 2 volts. So from here it is coming like 1 volt only, but in between, in the middle of the design, there is a noise of 1 volt, so that now the Y is 2 volts. Now how this driven element, how this buffer will recognize, that is simply it will check whether the value is less than or equals to like what I can say is it a valid input or not. Static discipline allows that for a valid input there will be a valid output. So here whenever the VIL value is 2 volts, which is like you can say maximum of 1 volt noise, this driven element can easily understand because it is a valid input, so that even though it receives 2 volts, it recognizes as a valid input only, so that it will produce the value which is the VOL, because each and every design follows the static discipline where that's VOL value is 1 volt. See, what I mean is between 1 plus 1 volt, whatever might be the value, it is a 1.11 or it is 1.5 volts, any value between 1 to 2 volts. If it receives between 1 to 2 volts, then automatically it will give you 1 volt only, because the VIL value is max VIL value is 2 volts only. If it receives 2 volts, then it will give you 1 volt. You can ask me, sir, for example, there is a nice voltage of 1.5 volts, then I'll get 2.5 volts now. Yes, I'll agree. If you get 2.5 volts, it is not a static, it is not a valid input, because for VIL, we have already mentioned it could be less than or equals to 2 volts. If it is more than 2 volts, it is not a valid input. So we are not giving the guarantee for an invalid input, we may give you the valid output. No. So our static discipline is for a valid input, there must be a valid output. That's it. Remember. Okay. Similarly, you can see now for logic 1 transmission. For logic 1, let's assume the value is 4 volts. Then let's assume the noise voltage of minus 1 volt. Then automatically the 4 volts becomes minus 3 volts. But still, if VIH is around 3 volts or less than or equals to 3 volts, the design, the driver, the driven element or the buffer can able to recognize which like as a valid input, then it will give you the valid output which is 4 volts. like that. So team, even though because of the noise X becomes Y, but because as the driver element, as the driven element, as the buffer is following the static discipline, whatever the Z you are getting from the Y, both X and Y are same only. You see this one, this one. So team, I want to give the conclusion. If the elements are all the elements present in your design are following the static discipline, don't then don't bother about the noise. Hurry sir, these many millions of gates, then might be noise may affect. No, then there will be changes. No, don't think in the other way, guys. Leave it, because all the elements present in your design are following the static discipline. So don't worry. If it is a valid input, you will get a valid output. So don't worry about the noise. In module 1 itself, we are telling you, forget about the noise if your design is following the static discipline. That's it. This is what about module 1, the fundamentals of digital abstraction. Now we will go to uh, just a second. Yeah, we'll go to another topic, I mean another module. Yeah, just a second. Yeah, yeah, yes team. uh, just a second, there is 1 volt. Yeah, now fine. Now team, we are entering into module 2, the MOSFET switch. Remember team, I'm not going to teach you the MOSFET or drain characteristics, transfer characteristics. They are from BTech. Remember guys, once again I'm telling you, people say we require basic electronics, digital electronics like that. Yes, I agree, but not entire digital electronics. And the way how you learned during your BE or BTech in undergraduation. Here, maybe the concept is same, but the way the approaches are different. You will understand when you enter into module 2. So remember, here in module 2, the MOSFET switch, we are going to discuss the topics which we haven't discussed till now, which we haven't covered in undergraduation studies. Remember. Now let's come to the point. Just a second. Yeah. Now, team, the switch. What is meant by a switch? Switch is a three terminal, like a switch which has three terminals, which is one input, output, and one control element. That is only a switch. Remember, even though diode is a, like diode can be operated as a switch, diode is not a ideal switch. Diode is not a perfect switch, because the third element is not present in the diode. It has only two terminals, anode, cathode. Whenever anode side voltage is greater than cathode side voltage, diode enters into on switch. I mean, on condition, it acts like a closed switch. Whenever anode side voltage is less than cathode side voltage, diode enters into off state. It behaves like a open switch, but that is not a perfect switch. Whereas you take either transistor or MOSFET, which has three terminals, in which one terminal is input and the terminal is output, and the third terminal is none other than control input. So here you can see a simple analogy. Before going to discuss about MOSFET switch, I want to show you how a switch works. Now you see here, yeah, here you can see now, here there is a switch, here there is a battery. Hope you can see my cursor. And here there is a bulb. Whenever the switch is closed here, then this voltage will be reaching this bulb through the switch, there will be current, like generation in the generation of the current in the circuit. Because of the current, yes, the light will glow. Whenever the switch is open, even though voltage is present, this voltage is unable to reach the bulb because of the open circuit. Then, even though voltage is present, because of the switch is open, the light will be off. That's what light bulb circuit with a switch and the lumped circuit element. Like symbolically try to represent. Team here in the same way, you can see the, just a second. Yeah. Now you can see the VI characteristics. Whenever the control input is zero, the third element I am saying, the control element. If at all control element is zero, team here, the flow moves from input to output. You can see here the current is zero because of the open circuit, but there will be a voltage. I repeat, whenever control input is zero, the current is zero, there will be a voltage across that. You can see here. Similarly, whenever the control input is logic 1, it acts like a short circuit. If it acts like a short circuit, the voltage across that particular element is zero only, because across short circuit, the voltage is zero. We learned from networks theory. However, what about the current? Current is non-zero because the current is flowing from input terminal to output terminal. However, voltage is zero. In the same way, here you can see for control is 1, the voltage is 0. Yes. Now, team, I want to conclude one point. Now, in this switch, whenever control is 0, current will be 0, but there will be a non-zero of voltage. Similarly, when control is logic 1, the voltage across that element is 0. However, there is a non-zero current. This is what the VI characteristics of a switch. Now, we are entering into the VI characteristics. Now you can see whenever control is 0, the voltage, I mean the current, the y-axis current is 0. That's why you can see horizontal line, current is 0. Whereas whenever the control is logic 1, you can see here, logic 1, there will be a rapid current increment in either of the direction. However, the voltage is x-axis value is 0 only. See here, that's why it's a vertical line. So I want to tell you one thing to the team. That is, whenever the control is 0, voltage will be 0. I mean, sorry, current is 0. Similarly, when control input is logic 1, the voltage will be 0. Remember, guys. Now, let's enter into the MOSFET. Guys, you can ask me, sir, why are you going for MOSFET? There is a BJT switch. No, you can go with BJT switch as well, right? Why have you entered into directly to the MOSFET? Yeah, I have genuine reasons. First of all, BJT is a asymmetrical device where emitter and collector regions are differently doped. That's why BJT is a asymmetrical device. Because of that reason, BJT occupies more space. Hence, in VLSI design, we don't prefer BJT. Whereas, you take FET or MOSFET, their source and drain regions are equally doped. Means, source and drain regions are same doping concentration. That means, you can use the source as drain as source. Hence, FET or MOSFET is a symmetrical device. FET or MOSFET occupies less space, because if there are two MOSFETs, you require only 5 regions. Means source 1, gate 1, drain 1. That drain you can use as a second MOSFET source. That means D1 or S2. Then again G2, D2. But whereas in BJT, if you want to fabricate or if you want to allot the space for the two BJTs, you require emitter 1, base 1, collector 1, emitter 2, base 2, collector 2. There you require 6 rooms, here you require 5 rooms. So in this a simple analogy, we can strongly say that BJT occupies more space, MOSFET occupies less space. That's the reason we don't prefer BJT. We are going to enter into MOSFETs directly only. And one more point. Coming to the BJT, as it is a asymmetrical device, you cannot use the source as like emitter as collector as a emitter. Whereas MOSFET can be considered as the source can be considered as drain can be considered as source. That means if it's a switch manufactured by the MOSFET, it is a bidirectional switch. You can give the input at the source, you can get the output at the drain, or else you can give the input at the drain, you can get the output at the source. Means remember guys, here the MOSFET is a bidirectional switch. Remember. Now let's come to the introduction to MOSFET. Here there is a MOSFET, you can see here guys. Guys, you can ask me, sir, here if there are dashed lines over here. Now here you can see my cursor. Here after the SiO2 layer gap, here there must be arrow marks now. If there are arrow marks, if it is a N channel or P channel, if that line vertical line is a dashed line, it is a E MOSFET. If it is a solid line, D MOSFET. That's we already covered in BTech, right? In basic electronics or microelectronics. Then here you have not shown anything. Simply you have drawn one MOSFET. Yes, we are from digital. There are different symbols for analog MOSFETs, digital MOSFETs. Here we are considering digital MOSFETs where we don't give any arrow marks. Instead, we give for P MOSFET, we give one circle at the gate terminal. For N MOSFET, we don't give any gate like a circle. Remember. And by default, we assume enhancement MOSFET only because of the power issue or whatever. Because by default, in E MOSFET, the voltage, the input voltage, let's assume 0, which is less than threshold voltage. Then the device will be in off condition only. Okay. That's the reason by default we assume E MOSFET only. Now let's continue. Guys, you can see the left hand side the MOSFET circuit symbol, and right hand side various operating voltages and currents. Now you can see there is a gate current, there is a gate to source voltage VGS, there is a drain to source voltage VDS, there is a current from drain to source IDS or ID. Guys, hope you know in MOSFET there is a silicon dioxide which acts like an insulator. Here MOSFET refers metal oxide semiconductor field effect transistor, MOSFET, or you can call this as a MISFET also, MISFET, metal insulator semiconductor field effect transistor, or else you can call them as IGFET as well, insulated gate field effect transistor. Now you know because of the silicon dioxide, because of the insulator, the gate current is 0 only. Remember, and the input voltage which is a VGS, whenever the input voltage VGS is more than threshold voltage, then only this device enters into on condition. So now I told you the very important point. Remember, being this MOSFET like we are assuming is a in enhancement MOSFET, definitely the VGS must be greater than VT. Then only the device enters into the on state. If at all your input voltage is less than VT, VGS is less than VT, then the device may not enters into on state. Because if the threshold voltage, you know, from the basic electronics, it is the minimum voltage required to form the inversion layer between the source and drain. Therefore, the charge carriers move from source to drain through the inversion layer. If the charge carriers are moving, obviously you get the current. So the required condition to become on is none other than simply the input voltage VGS must be greater than VT. That's it. Now you can see the VI characteristics as well. Now you see here the device is there, VGS and IDS, IG all are there. You can see whenever the gate terminal is having the VGS, you can see here guys, VGS is less than VT. If at all VGS less than VT, the device won't enters into on state. It remains present in off state. If it is present in off state, it acts like a off switch. If it acts like a off switch, what about IDS? Zero only. Because I told you, whenever the switch is off, current through that is zero only. Similarly, whenever VGS is greater than or equals to VT, then the device enters into on state. If the device enters into on state, the MOSFET can act like a on switch so that the current flows from drain to source. Hence, the current is from drain source, which is a IDS. However, whenever the MOSFET is in on state, the drain to source voltage will be zero because it is a short circuit. Hence, we have written here. You can see here VI characteristics. Whenever VGS is less than VT, IDS 0. When VGS is greater than VT, VDS is 0. Accordingly, we have given you the VI characteristics. Now you see VI characteristics of an N-channel MOSFET because there is no circle over there in the symbol. You can see here now. It is a N MOSFET only. Now this one. You see here, whenever VGS is less than VT, see here, then definitely it is like uh, current is zero only. Similarly, whenever that VGS voltage greater than VT, then definitely there will be a current because it acts like an on switch. There is a current. However, what about VDS? VDS is zero only. Yes, this is about the VI characteristics of a MOSFET. Some of you might having a doubt. I'll agree. Arey sir, whenever the switch is on, it has some finite resistance, right? Because every cell has a resistance. We can call this as a cell resistance. Then why are you ignoring it as a zero? Why don't you consider there is some resistance, finite resistance? Because of the finite resistance, you will get some voltage drop, right? V is equals to IR. There is a current. There is a finite resistance. There will be a voltage drop. No. Yes. Yes. I agree with your statement. Here in this MOSFET, there are two types of models. S model, SR model. S models means switch model. That means ideal. There is no resistance at all. It just acts like a either on switch, off switch. Whereas there is one more model called SR model, switch resistance model, where the MOSFET has some finite resistance when it is in on condition. That we will see later. But as of now, you just go through the MOSFET characteristics with S model only. Now, if it is S model, what about the static discipline? What about VOL value, VOH value, VIH value, VIL value? Let's assume for a NMOS inverter, you can see here, MOSFET switch, one NMOS inverter. Now you can see the first figure from left hand to right hand. The first switch is a just port representation, input port, output port. And as a MOSFET switch, which is an inverter, you can see the figure. At VDS, VDD, we are supplying the voltage VS, which is 5 volts, and we are measuring the output at the drain terminal. And we are applying the voltage at the input terminal of the gate, which is a V in. In a simplified format, we are giving you this, the rightmost figure. Now, from now onwards, if it is a MOSFET inverter, we use this symbolic way only. You can ask me, sir, how this MOSFET, how this circuit acts like a NMOS inverter. No problem. I'm here to clear your doubts. Yes, I'll be with you till completion of the PD concepts. Now coming to the point. If Vn is, let's assume, less than or equals to Vt, or let's assume Vn is 0. If, hope you can see the slides. Uh,
Yes, sir.
Team, are you able to see the slides? The MOSFET switch?
Yes.
Okay, now is the slide changed? Working
Yes, sir. It's
principle.
working principle. Yeah.
Okay, thank you. Yeah, coming to MOSFET switch team, here whenever the input voltage is less than V in, if the input voltage is 0, then the MOSFET is off. If the MOSFET is off, the current through the circuit is 0. If there is no current in the circuit, whatever the Vs here, you can see here, just a second. You can see here, this Vs voltage will appear here because there is no current in the circuit. So the voltage drop across this RL resistor is 0 only, because the current through this is 0. So you have given the input voltage as 0 and you got the output as 1. That means inverter. Similarly, you can see input is logic 1. Logic 1 obviously that will be greater than VT. If the input voltage is greater than VT, then the device enters into on state. If the design enters, the MOSFET is enters into on state, it acts like a closed switch, because I am assuming it as a switch model. So there will be a current flow. Here, as I am assuming it as a current S model, switch model, it acts like a short circuit. Across short circuit, the voltage is 0. We are measuring the output voltage at 0. At a drain terminal only, which is acting like a closed switch, on switch. So output will be 0 volts. Means whenever our input voltage is 1 volt, output is 0, because this acts like a closed switch, on switch. Then you will get 0 volts only across a short circuit. Hence, I can conclude that this circuit can behave like a MOSFET inverter. Remember, okay? Now, yeah. Now you can see just a second. Just a second, team. Yeah, working principle. Now you see, team, here just now like we have discussed, when Vn is low, logical 0, then switch acts like a off switch, you'll get the output voltage. You can see this one. I can move on. Now the inverter transfer characteristics. Team, now when you see the VI characteristics, transfer characteristics, whenever the input voltage is less than Vt, the device enters into off state. The output voltage is 5 volts, Vs. Whenever input voltage is more than VT, the device enters into on state. There is a maximum current flow, but output voltage is 0. Now, from this, we can relate static discipline, VOL, VOH, VIH, VIL, like that. For that, you can see what is the static discipline analysis using the S model. See, VOH. What is a VOH? What is a minimum value that you can get it at the output side being represented as logic 1? Obviously, VS. You got VS as well. Then from the circuit, remember guys, VOH will be VS only. Similarly, let's take VIL. What is VIL? The max voltage which can be represented as logic 0. Let's consider threshold voltage. If the threshold voltage is 1 volt, for example, whatever the voltage is less than 1 volt, less than threshold voltage, then definitely the device will be in off condition only, so that the MOSFET acts like a off switch, which can be considered as logic 0. Then if the VIL wants to be represented as logic 0, then definitely the value must be less than the threshold voltage. Or else, see, you take one, I'll show you one now. Just a second. Yeah. Now you see, guys, there is one buffer. There is one more buffer. See, I have transmitted logic 0. Now to this buffer, right side buffer, it must receive logic 0 only. But in between there will be a noise. Yes. But whatever might be the value that is getting, or whatever, that must be less than VIL only. If it is coming as a less than VIL, then for this driven element, that is still logic 0 only. Whatever the noise is included, nothing doing, no significance at all. So remember team, if any voltage to be recognized as a input logic 0, then the value must be less than VT. In a symbolic way, you can represent it as VT minus. That means whatever the VT value less than that. For example, if VT value is 1 volt, then it could be either even 0.9999 also, it's okay. But that must not be is equals to 1. So VIL value will be less than or equals to VT or VT minus. Similarly, suppose if this is the left-hand side buffer is transmitting logic 1, so that the device enters into on state. If the device wants to be in on state, this VT value must be, this VIL value or whatever if it is logic 1, it could be VIH. That VIH must be more than threshold voltage. Whenever it is more than threshold voltage, then only the driver element becomes on. Hence, the VIH value must be more than VT. Or if it is VT value is 1 volt, then VT value must be, VIH value must be 1.01 or 1.1 or 1.001. It must be more than VT. That is the required criteria for VIH. Then only that can be represented as logic 1. Similarly, guys, VOL. VOL means the output voltage. Here, what is the output voltage to be recognized as logic 0? To recognize as a logic 0, the output acts like a short circuit. That means VOL is 0 volts only. Means if someone asks you what is VOL, it is the output voltage of a design of a element to represent the output voltage as a logical 0. For that, VOL value must be 0. Like here, the VOL value is 0 volts. Remember, guys. So these are the static discipline values which you must denote. Similarly, now itself, we are going to have SR model, switch resistance model. In that case, what about VOH, what about VIH, what about VIL? That we want to know. That's it. And in the next class, we go for 2-input NAND gate, 2-input NOR gate, which has the better noise margin, everything. Okay. Now, just a second, team. Yeah. See here, team. I can say, just a second. Okay. I'll take only S model. Now, you team, you see here 2-input NAND gate. Let's take here A, B, M1, M2, output C. Let's start. When input is 0, what happened? When input is 0, just a second, guys, bear with me. Just a second, team. Then M1 will be in off condition. M2 will be in off condition. If they are off, it acts like an open circuit, no current flowing through the circuit. Then output will be high because it is giving Vs output voltage. Similarly, suppose if A input is 0, B input is logic 1, then definitely A input is connected to the M1. That's why M1 is off. Similarly, B input is logic 1. M2 gate is on. Then definitely, guys, see, combination of open circuit, short circuit is open circuit only. Even though M2 is on, as M1 is off, there is no current in the circuit, hence output is logic 1. Similarly, when input is like A input is logic 1, B input is logic 0, A input like M1 becomes on, M2 becomes off. Then also there is no current flowing through that, hence output is logic high. But whereas both the inputs are logic 1, then M1 is on, M2 is on. As both the circuits are on, then definitely, guys, the current flowing through there will be a current flowing through the two power supply rails, means between VDD and ground, between VS and ground, there will be a current. Yeah, just a circuit. Yeah. Here there is a current. As current is present, there will be a drop across a resistor or whatever, even across this one. As we are assuming switch model, the switch acts like a on switch only, short circuit only. So this is short circuit, this is short circuit. Then guys, you are measuring the output as across short circuit only. Hence, output voltage is 0 only. Now you see guys, here in front of you, there is one truth table for 0 0 combination one, for the combinations of input 0 0 0 1 1 0 1 1. The output is 1 1 1 0, which follows NAND gate only. So guys, remember, in NMOS technology, because we are considering N channel MOSFETs now. In NMOS technology, if at all the MOSFETs are connected in series, this is very important, team, because if the interviewer wants to know your basics, then guys, definitely they'll give you some little expressions, and they'll ask you to implement on NMOS or CMOS or PMOS. So remember guys, whenever they are connected in series fashion, then there will be AND operation. Okay, there will be AND operation. Now, because of this resistor, there will be complement. Hence, the NAND gate output expression, which is a C, is equals to, as they are connected in series, it is AND operation, means A dot B. Because of this resistor, complement whole bar. So this is AB bar. If at all they are connected in parallel, for example, later I'll show you the diagram. You can verify after this class. If they are parallel, then guys, just remember, it is OR operation only. If there is a resistor is present here, then definitely you get C is equals to A plus B. And because of that resistor, whole bar. Like this, guys. Now, I'll show you the diagram for 2-input NOR gate. But try to remember, guys, because in the next modules, we require all these things. If you don't study it right now, then it will be difficult for you when we go to another modules. Now you see here, 2-input NOR gate. And I'm giving you 2 to 3 minutes time. You write down AB, M1, M2, and output F. And you please correlate whether is it act like a NOR gate or not. Please cross check. Team, am I audible?
Yes, sir.
Okay. Okay, cross check, guys. Take your paper, pen and paper, and try to describe whether it is a NOR gate or not.
Yes, sir, it is.
Completed?
Yes, sir.
Huh. I think your name is Mini, right?
Yes, sir.
Yeah, Mini, can you explain briefly to the team?
Yeah, sure. Like
Yeah.
there can be condition when A and B are 0, 0. So
Hmm.
like then both will be 0, M1 and M2 will be off.
Hmm.
So the output will be the VS as 1.
Yeah,
F will be 1.
exactly.
And whenever like it is in parallel. So if A is if anyone is on that
Hmm.
time the current will flow to the ground. So output will be 0 that or 0 that time.
Exactly.
So
Exactly.
0110 and 1110 and 01 for all three conditions they will be 0 output.
Hmm. So it is similar to which gate?
It's NOR.
NOR.
Yeah.
Yeah. Good. Good, Mini. Good. Keep it going. Good. Now, team. So as I told you, whenever the two MOSFETs are connected in parallel, it replicates R operation. Because of the load resistor, you will get a complement because inverter. Okay. So it is a plus B whole bar NOR gate. Now you can try this one. Just a second. Yeah, you can see here multiple input NAND gate or NOR gates. You can see here. If they are connected in parallel or series, you need to understand. Now, can you try this? Not this. Yeah. Anybody, can you try this?
Yes.
Yeah, I'm waiting for you. Just show me the answer.
I think sir A and B will be in parallel and this parallel circuit will be in series with the C and D
No, Mini. Just
for the
if
second
you.
one.
No.
Just the
Just a
opposite,
second.
I guess.
What?
Like A and B is in series, and we need three parallel paths, and oh, each three parallel paths are connected to the same source.
No. Srihari, just a second. Just a second, Srihari. Instead of all these things, you just switch on your camera and show it to me. That's it. Mini, you also. You can see you, but let me guess. Because I want you to be as interactive as possible. Okay, as it is online class, if there is an interaction, then that will be good enough. Just a second. How to come back? Huh. Yeah, Mini, can you show? Where are you? Mm. Now, both Srihari and Mini, you can switch on your camera and you can show your diagram. Yeah, just a second. Yeah. Is this the first one, Mini? Okay. The next one? Okay, upside. Okay. Okay. Good. Good, Mini. Yeah, got it. Yes, Srihari or anyone else? What about Alorika, Mallesh, Pavan, Anusha? Shweta, Ramana, Pradyumna. Pradyumna, are you there? Okay, Srihari.
Hello.
Yes, Srihari. Can you show the diagram?
Uh, I'm I'm having an issue with the cam. Next from the next
Okay,
time
okay.
I will try to
Okay, okay. Not a
use a
problem. Not
virtual
an issue.
driver.
Okay, not an issue. It's okay.
Okay, but I have seen the figure right now, and actually I was trying to say the reverse, like
Okay.
uh, parallel for A and B. I mean the other way,
Mm-hmm.
like three parallel paths. I was trying to.
Okay. It's okay, Srihari. I understood. What you supposed to tell and you supposed to draw. I understood. Fine. Okay, Ramna. Okay. You have some cam.
To the drive. Just a second.
Means I thought of connecting A and B in series, and then the others in parallel.
Okay, okay. Okay, Srihari. Fine, fine. And what about the other people team? We, like during the session, uh, like you must involve in the class. Okay. Now let's get started. Now you can see here. Yeah, this one. So this is the solution team for N channel. Now the homework to you is next class you need to come how the PMOS 2 input NAND gate, 2 input NOR gate and respect to these expressions as well. Means AB plus C plus D whole bar, A plus B into CD whole bar. I want the PMOS structures because in the next class we are entering into CMOS. Okay. So you come up with the PMOS and later we'll go to SR model and then you can see here guys all are there and we have so much to discuss about MOSFET only, conclusions, everything. Okay. Now no problem at all. Now here I'm stopping here guys. Okay. And in the next class you come with the PMOS circuits. We'll continue the remaining topics present in module 2. I told you guys whatever the modules you are going to have the concepts and all, these are very helpful to you when you enter into physical design, which is a synthesis, PNR and STA. I'm sure you realize over there. I can tell the same. Here I'm not at all taking any drain characteristics, transfer characteristics and all, which you have discussed already in your BTech academics. Here we are not taking all these things. These are entirely different concepts. These are from PD concepts only. That I can tell you proudly. Okay. Now it is doubts clearing sessions. Questions. Do you have any doubts, guys? Oh, no questions. Slide. Anyway, any questions, guys? If you have any questions, you can ask me now.
Thank you, sir.